Hello everyone and welcome. I'm excited to kick off today's presentation. The title of our talk is Innovative Strategies for Business Growth, with a subtitle of Unlocking Potential in a Competitive Market. Over the next few minutes, we'll explore key strategies, insights, and practical tips to help your business thrive. Let's get started. Let's take a closer look at the turboprop engine. This type of engine is a fascinating blend of efficiency and power, making it ideal for many regional and small commuter aircraft. Unlike pure jet engines, turboprops use a combination of a turbine engine and a propeller, which allows them to operate efficiently at lower speeds and altitudes. The key advantage here is their fuel efficiency, which helps reduce operating costs for airlines. Additionally, turboprops can take off and land on shorter runways, giving them a lot of versatility. When we think about their role in the overall theme of aviation technology, turboprop engines exemplify how innovation can optimize performance and sustainability. They are a perfect example of engineering that balances power, economy, and environmental considerations. This makes turboprops an essential part of modern aviation's evolution, especially in connecting smaller destinations efficiently. Let's take a closer look at some key components involved in turbine systems. First, we have the free turbine, which operates independently of the power turbine and is often used in helicopter engines to provide smooth power transmission. Next, we have gear-coupled turbines, where gears connect turbines to other components, allowing for efficient power transfer and control. Reduction gears are crucial because they reduce the high rotational speed of the turbine to a more manageable level for the propeller or other output devices. Speaking of which, propeller controls are essential for managing blade pitch and ensuring optimal performance and safety during operation. That brings us to overspeed safety devices, which are safety mechanisms designed to prevent the turbine or propeller from spinning faster than safe limits, protecting the entire system. And all of these components work together in a sequence, which is vital to ensure smooth, reliable, and safe engine operation. This sequence helps us understand how each part interacts within the overall system. Let's start by looking at the basic components of a gas turbine engine. It has a compressor, which compresses the incoming air to increase its pressure. Then, this compressed air enters the combustion chamber, where fuel is added and burned to produce high-energy gases. These gases then pass through the turbine, which extracts energy to power the compressor. Finally, the exhaust nozzle directs the remaining gases out of the engine, producing thrust. Now, a turboprop engine is a bit different. It's actually a combination of a gas turbine engine plus a reduction gearbox and a propeller. The gas turbine provides the power, but instead of driving a fan directly like in a jet engine, this setup uses a reduction gear to turn a propeller. Importantly, a turboprop operates in the same fundamental way as any other gas turbine engine. The core principles of compression, combustion, and expansion are all there. What makes the turboprop unique is that the turbine usually has extra stages. These additional stages are designed to extract more energy from the gases so that it can drive the propeller efficiently. This design allows turboprops to be very effective for certain types of aircraft, especially those that need good fuel efficiency and the ability to operate at lower speeds. So, in summary, whether it's a pure gas turbine or a turboprop, the underlying cycle remains similar, but the turboprop adds these extra stages and a propeller to adapt the engine for specific flight needs. Now, let's take a closer look at the two main types of multiple-stage turbine configurations found in turboprop engines. The first one is gear-coupled, which is also known as a fixed turbine setup. In this configuration, the turbine is directly connected to the gear system, and they rotate together as a single unit. This setup is quite straightforward and provides a reliable way to transfer power from the turbine to the propeller. The second type is the free turbine. Unlike the fixed turbine, the free turbine is not directly connected to the gear system. Instead, it operates independently, with its own turbine wheel that drives the propeller through a separate shaft. This separation allows for more flexibility, especially when it comes to controlling power and managing different engine speeds. Both configurations have their advantages, and are chosen based on the specific requirements of the engine and the aircraft. Understanding these differences helps us appreciate how turbine engines are optimized for efficiency and performance in various operating conditions. This concept of turbine configuration is fundamental as we explore the overall design and functionality of turboprop engines. In a gear-coupled fixed turbine engine, all the turbine stages are connected to a single shaft. This means that instead of having multiple shafts, everything is linked together on one main shaft. Now, this shaft has a dual role. It not only drives the engine compressor, which is essential for maintaining airflow and compression, but it also turns the propeller. To make this work efficiently, a gear reduction gearbox is used. This gearbox reduces the rotational speed of the shaft before it turns the propeller, ensuring the propeller spins at an optimal speed for thrust and fuel efficiency. This design is particularly important because it allows the turbine to operate at high speeds while keeping the propeller at a manageable, efficient speed. It's a clever way to connect the turbine and propeller mechanically, making the whole system more compact and reliable, which aligns with our overall focus on efficient engine design. This slide doesn't contain enough information. That's why we're moving to the next slide. In a free turbine setup, you'll notice that the turbine stages are connected to two completely independent shafts. This is a key feature because it allows for greater flexibility in how power is transferred. One shaft is dedicated to turning the engine compressor, which is essential for maintaining engine airflow and pressure. The other shaft is responsible for turning the propeller, and this is usually done through a reduction gearbox to match the optimal speed of the propeller. It's interesting to note that while 3 turbine stages are typical in many engines, there are designs that use up to 5 stages. These additional turbines are used to drive not just the propeller and the core rotor elements, but also various accessories. This multi-stage configuration provides the necessary power for all these components, ensuring smooth operation and efficiency. Connecting these points to the overall theme, the free turbine concept offers a lot of advantages, especially in terms of engine efficiency and flexibility. It allows different parts of the engine to operate independently, which can lead to better performance and easier maintenance. This setup is a great example of how engineering can optimize power transfer in aircraft engines. This slide doesn't contain enough information. That's why we're moving to the next slide. Both of these configurations have been used successfully in turboprop engine design. This means that engineers have explored different options and found effective ways to optimize performance. It's important to recognize that each configuration offers unique advantages, and choosing the right one depends on the specific application and design goals. These successful implementations highlight the versatility and adaptability of turboprop engines, which is a key theme in our overall discussion. Ultimately, understanding these configurations helps us appreciate the engineering choices that lead to efficient and reliable engine performance. Let's take a closer look at turboprop controls. These controls are essential for managing the engine power and ensuring smooth operation. First, we have the power lever, which adjusts the engine's power output. Moving it forward increases power, while pulling it back reduces it. It's important to make these adjustments smoothly to prevent sudden changes that could affect the aircraft's stability. Next, there's the condition lever, which typically controls aspects like propeller pitch and sometimes mixture settings, depending on the aircraft. Proper handling of this lever helps optimize performance and efficiency. We also have the propeller control, often a lever or a knob, that adjusts the blade pitch angle. This is crucial for controlling thrust and managing engine loads. Finally, the feathering control allows us to align the blades with the airflow in case of engine failure, reducing drag and preventing further damage. Connecting all these controls is vital for safe and efficient operation, especially during different phases of flight or in emergency situations. Understanding how these controls interact helps pilots manage the turboprop engine effectively, which ties back to our overall theme of aircraft systems management. Let's take a closer look at the propeller control system. It is divided into 2 main types of control. Flight operation and ground operation. During flight, the propeller blade angle and fuel flow are automatically governed based on a predetermined schedule, which helps maintain optimal engine performance and efficiency at various power settings. However, there's an important point to remember. Below the flight idle position of the power lever, this automatic schedule, the coordinated RPM blade angle, becomes less effective. At this stage, the engine enters what we call the beta range, which is primarily used during ground handling. In the beta range, the control of the propeller blade angle shifts away from the governor. Instead, it is directly controlled by the position of the power lever. This allows for more precise management of the propeller pitch during ground operations, such as taxiing or reverse thrust. Speaking of reverse thrust, when we move the power lever below the start position, the propeller blade pitch reverses. This action is crucial for rapid deceleration after landing, helping to slow down the aircraft efficiently and safely. So, understanding these control modes and their respective applications is key to operating the aircraft smoothly and effectively in both flight and ground scenarios. Now, let's talk about fuel control. The turboprop fuel control and the propeller governor are actually connected and work together in coordination. This means they're constantly communicating and adjusting to ensure smooth operation. The power lever plays a key role here. It sends a signal from the cockpit to the fuel control, telling it how much power we need from the engine. Together, the fuel control and the propeller governor establish the right combination of RPM, fuel flow, and propeller blade angle. This coordination is essential because it creates the necessary propeller thrust to keep us moving efficiently. So, in essence, these systems work hand in hand to make sure we have the right power output, fuel efficiency, and optimal propeller performance, all critical to the overall operation of the aircraft. Power changes are affected by changing fuel flow. When we increase the fuel flow, it causes the turbine inlet temperature to rise, which means more energy is being introduced into the system. This additional energy allows the turbine to absorb more power. As a result, the turbine transmits this increased energy to the propeller in the form of torque. Now, to handle this increased torque and keep the engine running smoothly at a constant RPM, the propeller blade angle is increased. This adjustment allows the propeller to absorb the extra torque and generate more thrust, maintaining stable engine operation while providing the necessary power for flight. This process highlights how fuel flow control directly influences engine power and thrust, which is central to understanding how jet engines respond to different power demands. Let's take a closer look at the reduction gear assembly. This component is critical because it helps control the speed and torque transmitted from the engine to the machinery. Essentially, it acts as a kind of gearbox that reduces the high rotational speed of the engine to a more manageable level for the equipment to operate efficiently. Understanding how this assembly works is key to appreciating the overall reliability and performance of the system. It involves precise gear ratios, which are carefully selected to optimize power transfer while minimizing wear and tear. By ensuring the gear assembly is properly designed and maintained, we can improve the longevity and efficiency of the entire setup. This ties into our broader goal of creating reliable, durable machinery that performs well under various conditions. So, the reduction gear assembly isn't just about gears. It's about ensuring smooth operation, efficiency, and durability in the overall system. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. The function of the reduction gear assembly is to take the high RPM generated by the engine and reduce it to a lower, more manageable RPM for the propeller. This is crucial because engines often run at very high speeds, but propellers can't safely operate at those levels without risking damage or inefficiency. By using a planetary gear reduction, most assemblies can achieve this reduction smoothly and efficiently. Additionally, many gearboxes include a propeller brake. This brake is designed to prevent the propeller from windmilling when it's feathered in flight, which helps reduce drag and saves fuel. It also plays a key role after engine shutdown, decreasing the time it takes for the propeller to come to a complete stop. All these components work together to ensure the propeller operates safely, efficiently, and in sync with the engine's performance, which is essential for reliable aircraft operation. Let's take a closer look at the turbopropeller assembly. The turbopropeller plays a crucial role in aircraft performance because it provides an efficient and flexible way to utilize engine power across different flight conditions, especially within the alpha range, which is during normal cruise. Now, when we need ground handling or reveering, which falls into the beta range, the propeller can be operated differently to generate zero or even negative thrust. This flexibility is essential for maneuvering on the ground without relying solely on the engine power. The major subassemblies of the propeller include several key components. For instance, the barrel and dome are structural parts, while the low-pitch stop assembly and overspeed governor help control blade angles and prevent overspeed conditions. The pitch control unit manages blade pitch adjustments, and the auxiliary pump ensures proper hydraulic operation. Other important parts are the feather and unfeather valves, which are vital during engine failure scenarios to reduce drag, and the torque motor that adjusts blade pitch. The spinner, which is a cone-shaped assembly, mounts on the propeller and covers the dome and barrel. Its design helps streamline the assembly and reduces aerodynamic drag. Additionally, the de-ice timer prevents ice buildup, and the beta feedback assembly provides feedback to control systems, ensuring smooth operation during beta range. Modern turboprop engines use dual full-authority digital engine control, or FADEC, to precisely manage both engine and propeller functions, enhancing safety and efficiency. Finally, the spinner assembly's cone shape not only encloses the dome and barrel, but also helps streamline airflow around the propeller, minimizing drag and improving overall aerodynamic efficiency. All these components work together seamlessly, contributing to the propeller's versatile performance and the overall efficiency of the aircraft. This slide doesn't contain enough information. That's why we're moving to the next slide. On this slide, we're looking at the synchrophasing system, which is designed to keep a specific angular relationship between the master propeller and the slave propellers. This synchronization ensures smooth operation and reduces vibrations, contributing to overall aircraft stability. The propeller operation is primarily controlled through a mechanical linkage, running from the cockpit-mounted power lever, and if equipped, the emergency engine shutdown handle, to the coordinator. From there, it's linked to the propeller control input lever, allowing the pilot to manage propeller pitch and speed effectively. In more modern aircraft, you'll find that electronic throttle control systems are used, which are connected to the FADEC controller, full authority digital engine control. This setup provides more precise and automated control over engine and propeller operations. Turbopropeller control assemblies include a feathering system. Feathering is crucial because it allows the propeller blades to be turned edge-on to the airflow if the engine is shut down during flight, reducing drag and preventing damage. The good news is, during flight, you can unfeather the propeller if you need to restart the engine, restoring thrust quickly. Finally, it's important to note that control systems in large turboprop engines differ from smaller ones. Larger engines use dual acting systems, which rely on hydraulic pressure to adjust the blade angles, providing the power needed to handle the increased size and complexity of these engines. This hydraulic assistance ensures precise control and safety across a wide range of operating conditions. Now, let's turn our attention to overspeed safety devices. These are critical tools designed to help prevent accidents caused by speeding. Essentially, they act as a safeguard by monitoring vehicle speed and intervening if it exceeds preset limits. The most common types include speed governors and electronic control systems. Their main purpose is to ensure drivers stay within safe speed ranges, especially in sensitive areas like construction zones or school zones. Incorporating these devices into our safety protocols not only helps protect drivers and pedestrians, but also reinforces a culture of responsible driving. As we've seen throughout this presentation, Managing speed is a key component of overall safety, and these devices are an effective way to support that goal. Overspeed occurs when the actual engine speed exceeds the desired engine speed, which is set on the propeller control by the pilot. To prevent this, we have the overspeed governor, acting as a backup for the main propeller governor. It's mounted on the reduction gearbox and features its own flyweights and pilot valve. When the propeller RPM goes above a preset limit, specifically more than 100% of the desired speed, the overspeed governor activates. It does this by releasing oil from the propeller. This release of oil causes the blades to move to a higher pitch angle, which in turn reduces the RPM back to safe levels. It's important to note that the overspeed governor is adjusted during installation and cannot be adjusted in flight. There are no cockpit controls for it, meaning it operates automatically to protect the engine and propeller from overspeed conditions. Overall, this system adds an essential layer of safety, ensuring the engine runs within safe limits even if the main governor fails or if there's an unexpected surge in RPM.